Hey everyone, it is Friday, June 7, 2019. Time's about 07:45. It's 64 degrees Fahrenheit out, and it's sunny and rain-free, and it's nice. Today I'm going to talk about the Sibley group, and I'm going to talk about the Belt supergroup out west. Now, many of you know, back in May, I was in Ontario around Lake Nipigon, where the Mesoproterozoic sediments of the Sibley group were deposited. Now, these are intracratonic, meaning within the continent deposits, and likely represent lake deposits. Okay? Now, it's a weird basin. It's not a very big basin. Lake Nipigon is big, but it's not huge, not like the Belt supergroup. And it may have been more extensive, but it's Mesoproterozoic, like I said. And so is the Belt supergroup, which is much thicker. The Sibley isn't even a kilometer thick. All right, as where the Belt supergroup is between 10, 15, even 16 kilometers thick in places. So it's a lot thicker, magnitudes thicker. But they were deposited around the same time. And what I've been doing is, this is my GeoLab book. I have my field books. Those are those yellow books that I take out in the field, and I did some creeping around the Sibley. I went to Sibley Peninsula, which is where the sleeping giant is. Did some creeping around there to look at the rocks and whatnot. And we are going back to Glacier National Park in September. So I'm kind of doing research and background and trying to see. Now, what I've done so far is I've taken the stratigraphy of both, and what I do in my lab book is I write down any of the references I use, full references, if I'm utilizing them. When I'm describing rocks, I don't do this, and those are in here too. And I'm trying to use basically our known paleomagnetism data, along with the dating that has actually occurred within both the Sibley and the Belt supergroups, both detrital zircons and direct zircon, because both of these, the Sibley does have igneous intrusions within it as well. They both have igneous sills and dikes within them. My last video, or I'll link the video below, we actually go to a Sibley group outcrop with a igneous sill in it. So it took me a minute to remember that. I'm getting old. But so anyway, I took the dates, and here on the left, and I just made a column, and on the right I narrowed it some more. This is the Sibley group. This is the Belt supergroup. But Belt supergroup. And as you can see, we're not dealing with a huge chunk of time. The Belt supergroup, we're dealing with about 1,380 million years to about 1,478 million years ago. And now the Sibley group, being as thin in lake deposits, it would take a longer time for it to be deposited, but it wouldn't take this long. So I redid it a little bit, and I think that's a more accurate representation based on our present knowledge of when they were deposited. Now, this is temporal. I'm chronologically correlating them when they were deposited. They are not lithologically correlative at all. The Belt supergroup, which I'm going to get in here in a minute, is a little on the weird side. And we know the Sibley group was deposited in lake deposits, all right? And it was a small intracratonic basin. The Belt supergroup seems to be a large intracratonic basin. Just to give you a sense of the size, and here's a correlation chart of the Belt supergroup with here. This is it correlated over. This is my drawing. This is Montana, Idaho, British Columbia, Alberta. Washington's over here. And you can see, hopefully, basically the Belt supergroup, it's called the Purcell group in Canada, forms this triangle here. Okay? And that's significant, I think. It's important. And here's basically the correlation along that line. The colors will tell you the basic different types. The lithologies are more complex than this, but that's basically what's doing. The reason why I did this is because I was trying to see, we still debate what kind of environment this thing was deposited in, the Belt supergroup. It doesn't seem to be marine deposit, not even a cratonic sea, not even in inland sea like we saw through the Paleozoic in North America and the Mesozoic out west. It doesn't seem to be that per se. See, the thing with the Belt supergroup is Even the small Sibley group in Ontario has a major unconformity within it. The belt supergroup is lacking in these unconformities. It's essentially continuous to the whole 15 kilometers plus or minus of it. So we had a basin subsiding continuously with switching between clastic sediments being taken in from the east. There's almost no sedimentation from the west, which is also really weird, but I'll get into that in a second. And carbonate deposits, which came in either from the west or the east, or the north or the south, when classic influence stopped. So it's just really weird because the sequences we see in the belt supergroup do not look like modern passive margin or cratonic marine sediments. And we can sit there and say, well, was the Mesoproterozoic, blah, 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 but plate tectonics was in action, and it probably wasn't exactly like modern plate tectonics, but it was close, okay? So we know that was going on. We know rodinia was forming. It would break up, about 1.4 billion years ago is when this stuff was deposited. So about 1.1 it started to break up, roughly around there. So we know we had plate movement. So we had modern analogs, and we have passive margin sediments of the Huronian supergroup in Ontario that are far older, about 1 billion years older than these intercratonic deposits, and it shows a normal passive sequence on the side of a rift. So we had modern geology in operation then, which is something we didn't have in the Archean. Okay, plate tectonics anyway. So what caused this triangle type thing to be deposited? Well, it does seem some other deposits are marine. Now, see, the thing with the Mesoproterozoic is we have no macrofossils. Okay, there's no trilobites, there's no gastropods, there's no bivalves or clams. There's none of this stuff in these deposits to determine whether they were marine, freshwater, or tidal flat, or any of that. All we have are stromatolites, and stromatolites need warm, stable, very shallow conditions to grow. They can be fresh or saltwater. Well, in the Precambrian, they could be. They still are, but anyway, it's a rant for another time. Anyway, so there's massive stromatolites, and I mean, the Apicuni, I believe it, or not the Apicuni, the Alton Formation, which I visited last year, and we climbed up the hill, and I did a whole and showed you the beautiful stromatolites in it. That's on the order of, in glacier, 840 feet or 256 meters. That's a lot thicker than a lot of the Phanerozoic carbonates, okay? 2 or 3 times thicker. So we had consistent basin subsidence while these stromatolites were growing, and as they would grow, it's not really a reef environment because reefs didn't exist then. But it clues us in that there was consistent, stable sedimentation. There's also some evidence of some tectonic activity, like we see things like, slide breccias and stuff like that had to happen during deposition, and that's a key thing. It's not major, but it kind of tells you what the basin is. Okay, this is going to get way too long. It's going to approach 10 minutes, so I'm going to try to nip this in the bud. What kind of environment would the belt supergroup deposited in? Like I said, it was a triangle. There probably was a sea that came in from the northwest from time to time. Okay, and this is not a Yellowstone type caldera environment under the belt supergroup. We actually had one of those at the time in North America, the St. Francis Mountains in Missouri, okay, the Ozarks, and that would slowly migrate under what is now Illinois in the Illinois basin, so it head east, but that's not what's happening here. I think what was happening here is you had crustal extension caused by, this basin was subsiding. The craton there, the lithosphere at the time would have been a little thinner than it is today, but that would have been some old continental rock that hadn't done much. And if you look at the paleomag data, North America doesn't move very much during the deposition of the belt supergroup and the Sibley supergroup. So relative to everything else on the planet, this was kind of stationary. Okay, so it would have subsided more and more, and probably the same thing with the Sibley. It would have subsided just because it was old. And as it did that, there probably was some melting in the magma, causing the crust to thin. Okay? As the crust thinned, you would get magmas injected up through this belt supergroup as it was being deposited. Something similar to the Sibley group, but that happened later and is associated with the mid-continental rift. There's no rift associated with the belt supergroup. At least we don't think. So as this crustal thinning occurred, usually, and this magma melting, usually what you would get is you would get the formation of a triple junction, an upside down triangle, which looks like a rift. Okay, and this is a large enough area to have formed such a triple junction. I think a triple junction may have began to form in the basement rock. We don't have anything that goes that deep, that goes 20 kilometers down in the area, but I don't think it was caused by a rift, because as the continental crust began to sag, then thin, and cause minor melting, there was no plume to come up and actually rift it. All right, there was probably subduction going on to the west, but that subducting plate wasn't under the belt supergroup, so it couldn't form a plume in the deeper mantle and couldn't actually rift. It started to form the makings of rift, but instead of that, instead of a rift, what you ended up was actually rapidly, geologically speaking, within 90 million year time span of a rapidly subsiding. I mean, 90 million years to deposit 15 kilometers of sediment is a lot. I mean, there's Phanerozoic deposits that are that thick, but that's over 200 million years. So this was fast. So I think that's kind of what happened. So it wanted to rift, and it would have rifted if there was a plume to come up into it. It started to form the triple junction. You can get triple junctions if this hypothesis is true without actual rifting occurring. You don't need a plume to form the triple junction. I mean, a plume coming up forms the triple junction. You get the magma plume coming up, and it will crack and form a triple junction. But you know what else will form a triple junction? Basin subsidence. So instead of the crust bulging, it goes this way. That would also form a triple junction. It's just one that doesn't rift. But anyway, so it's very interesting, and like I said, in September we have a lot more work to do. I will show you guys this stuff again if you want. I'm going to try to get a permit to actually collect rock samples from Glacier National Park this year, and hopefully I will be able to study the lithology in detail. But and the reason why I do this on occasion is because marker bleeds through. So anyway, that's it. If you have any questions, leave them below, and I hope you learned something.